Our sun emits different kinds of radiation. One of the most difficult to study is neutron radiation. Unlike electrons and protons, neutrons don't have an electric charge, and they can pass through many kinds of solid objects without being scattered or absorbed. This makes it difficult to build devices to detect them. In the past, most neutron detectors use helium-3, which is usually made as a byproduct of nuclear weapons production. After the end of the Cold War, weapons production decreased, and there is now a worldwide helium shortage, so we need to research different materials that we can use to make neutron radiation detectors. In the UNL Detector for Analysis of Solar Neutrons project, or DANSON, researchers at the University of Nebraska-Lincoln are studying effects of solar neutron radiation on two types of materials at the International Space Station.
Well, there are several applications we can have with these neutron detectors. One is if these detectors work, they can help as a neutron voltaics. So same as you have photovoltaics where you receive light from the sun and you produce some electricity, we could have something similar, but instead of working with light, we will work with neutrons. So we will capture some neutrons and we are able with these materials to generate some electricity. This is important because, for instance, if you want to send a shape to the space, you don't want to carry a lot of batteries, right? So if you can generate this current, this electricity in the space while the astronauts are traveling without any additional battery, that's one of the applications we want. At the same time that we are protecting the astronauts from the radiation coming from the sun, because these detectors, they will capture all the neutrons coming from the sun, so we will protect the astronauts as well. Neutron detectors are also used to treat cancer, so we are working with small pieces of detectors. So if we can make detectors that are smaller and smaller, we can introduce these detectors inside of our body to treat or detect cancer.
Solar neutron radiation emitted by our sun can be damaging to materials in space like communication satellites, and they can be harmful to astronauts. And so it's important to be able to detect those things. So what we're looking at for this experiment is the materials that contain lithium-6 and boron-10. We're specifically looking at solar neutron radiation. And because neutron radiation from the sun tends to interact with particles in the air and break them apart and create sort of secondary radiation, we're looking to actually get above the atmosphere that sort of filters out and obscures that signal. So that's why we want to be on the space station.
Okay, so neutrons are really difficult to detect because they don't have any charge. So it's difficult for them to leave like a mark on the material. So what we do is we use a material that has specific elements that once they interact with the neutron, they will decay in different particles. These particles are charged and they can leave a mark on the material.
Basically, the way the cube's designed, and you can kind of see from the front, there are those little pockets where we had detectors placed. So I'm going to turn to the side. So you can't see inside from here, but basically they go from one diagonal to the other. So that way we're getting different depths. The cube itself is a moderating material, which means that it's just designed to like decrease the energy and slow the neutrons down. Because the way that what we're looking at getting is how much these neutrons actually come into the cube based on where the detectors are located and how much radiation they received.
We have our sample and we have a small circles of gold. Each circle will be one detector. So in this particular sample we have about 18 to 21 different detectors.
Fill station on 2 installed a neutron detector, and the view's up if you haven't.
So we were on the space station on a Sunset hatch in Node 2 from October of last year to March. And so now we have the experiment back. We've removed all the detector elements and we're currently analyzing them right now.
So we can have different IV and CV curves from each detectors we are working with. So these detectors have one side where we can capture the neutron. So this side will be made of boron carbide and or lithium tetraboron. And the other side is silicon. So the idea here is that once we capture one neutron with the boron carbide, it will create some particles that are charged. These particles are moving through this material and they will create some electrons and holes. We can collect the holes in one side and the electrons on the other side. So somehow after the neutron capture, we are collecting some current, and measuring that current, we will know how many neutrons we capture.
Yep, so basically we have like a back contact, and then we have, depending on the sample, it really depends on which one it is, a different amount of contacts on the top. And we usually keep the back contact hooked up, and then we just basically swap out the top wire and just measure IV curves and CV curves for each little diode on there.
Okay, so the IV curves are the current as a function of the voltage, and the data we're looking for changes in the width and orientation of the graph to understand how it's degraded over time. And the CV is the capacitance versus as a function of the voltage, and we're looking for how that'll also shift, and they'll both be analyzed by Jen and backtracked to show how much they've changed over the time.
For the simulation, basically I have a virtual version of the cube, and I tell Jayon what material I'm using and what dimensions and where everything is located. And then from the SDK software, where we have information about how much like direct sunlight we're getting, because we're not looking at light, but we are looking at neutrons. And that way, when I'm using the simulation, I can put in exactly how much we're expecting to come from the sun, and eventually compare what happens in the simulation versus what we actually read in the detector, and kind of work backwards and see how many neutrons we saw and at what energy levels.
Now that the DANSON experiment has returned from the ISS, UNL researchers hope what they learn will help in developing small, effective neutron detectors for use on Earth and in space. By examining the distribution of neutron captures in the moderator, they also hope to catch a glimpse into the nuclear fusion processes that fuel our sun.
My name is Elena Echeverria, and I am almost a doctor in physics. I'm 1 month far from that, and I've been working in this project since 3 years ago.
I am a senior undergraduate in physics and mathematics, and I've been working on this project for about 19 months.
I'm an undergraduate and I've been working on the project for a little over a year.
My name's Ian Evans. I'm in my undergrad, and I came to the program through my advisor.
I'm Ben Swanson, and I applied with Ian through our professor.
Now that's Nano.